all good. I should be able to walk. One would think. Yes. Yes, I want to mention labs this week. We may or may not get to a lab this week, which is to say we spent a bit more time on the math than I'd anticipated, which is fine. Like, I'm delighted with that. But as a result, I just don't know if we'll be at a place in the teaching where I want to do a lab yet. If we do, it'll be Thursday or Friday. It definitely won't be Wednesday. So we'll see how quickly we move through these notes. I don't want to rush it. This stuff is so foundational, I would rather push a lab off. Or what we may do is we may do kind of a non-chemistry lab. We may do a lab this week where we model some of the stuff we're learning here using sort of physical manipulatives. Anyway, I'm not entirely sure yet. Just where the Monday is falling in the lesson cycle is not where I expected it to be when I planned out the lab schedule. So I'm not sure what we'll do for lab this week. I'll let you know by tomorrow, or at least for sure by Wednesday. I would say we may not do a lab this week. If we do it, we'll, bless you. If we do it, will be a simple one. Does that make sense? Anyway, for today, we're now going to use some of this math and use some other things. This unit is all about quantities in chemical reactions. All right? So by the end of it, you should be able to predict not just the product of a chemical reaction, but you should actually be able to say how much of everything you'll get. If I give you 5 grams of a compound and say burn it, you should be able to tell me not just what will happen to it, but how much the end product will weigh. Does that make sense? And like many things in life, this is easy to say and tough to do. So like, let's just look at a simple example. If I had solid magnesium, well, that's a red pen. That's not what I wanted. If I had solid magnesium and I react it with oxygen, what am I going to write? Plus what? O2, because of course oxygen is diatomic. Good. And what state of matter is oxygen? Gas. Great. What am I going to get as a product? What am I going to get? Yeah, and of course you get that because Mg takes what charge? 2 plus, and oxygen takes 2 minus, and so those balance out charge-wise just as you said it. Yeah, very good, MgO. So in my mind, that was going to be like a really elegant moment. You'd be like, MgO, I'd like to see, but it didn't work that way, and that's okay. And that's probably going to be a solid. It's an oxide. Is this balanced? How do I balance it? Good. We need 2 MgO to give us enough oxygen, and that means that we need 2 magnesium to give us enough magnesium. Okay, good. Now, this reaction tells us that 2 magnesium atoms should react with a single oxygen molecule to produce 2 formula units of magnesium oxide. And just for the sake of argument, if I did the same reaction, but instead of having 2 magnesium, if I had 4 magnesium, what all would happen? Who could talk me through that? So could I do this whole thing, but instead of using 2 magnesium, could I use 4? Sure, what would I get? So 4 magnesium, how much oxygen would I need then? Good, so instead of 1 oxygen, I'd now need 2, good. And then what would I get as a product? 4 MgOs, good. Does that make sense? You don't need to necessarily write this, but just for the sake of argument, whoa. I could say, okay, 4 magnesium could react with 2 oxygen, that should be capital, of course, to give me 4 magnesium oxide. So it's easy to manipulate that. If I wanted to use 200 magnesium, could I? Sure, what would that look like? 200 magnesium, yeah?
You have 100 of the oxygen molecule.
Good, and how much magnesium oxide do I get? 200, good, very good. Does that make sense? So the chemical formula, the chemical equation gives us lowest terms, but we could easily scale it up. And that's important, and it's important for this reason. I can't count out 2 magnesium atoms. Why not? Why can't I count out 2 magnesium atoms? Yeah, why not? I mean, why can't I just go in the lab and get my tweezers and get out 2 magnesium atoms and react them? Yeah, because they're tiny, right? They're really, really small. So in practice, if you look here, this is an example of a pretty big molecule. This is called Pentacene, and it's carbon. It's really cool, actually. It forms into these interlocking rings like that. So it's carbon making all these rings. That's each of the black spheres, and each of the white spheres is a hydrogen. It's called Pentacene. Only in about the last 10 years have we been able to make a microscope sensitive enough to actually see individual molecules. And it's incredibly, incredibly difficult to do. But if you look on the right, that's a pretty incredible thing. That's a micrograph of actual individual molecules. Tiny, 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 tiny. We've just now gotten the ability to be able to see those individually. Can I manipulate them individually? Go in and move them around? No. We just don't have an instrument anywhere in the realm of fine enough to manipulate that. Right? And I've gone on the "we're really big" spiel a bunch of times. I wrote this note over the summer, and I thought it'd be a big revealing moment here, but then I think I've used this same spiel about 30 times. You can take a look at it at your leisure and use it to like wow and amaze your friends. But there's more molecules of water in a human tear by a factor of about 100 million than there are people who've ever lived. These things are really, 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 really tiny. So this all leaves us with a problem. And you can go to the next page. That first page is all just introductory. So the solution to our counting problem is to use a counting number. Yes, sir. Is that a hand? Oh, you're just gesticulating wildly. I understand. So the solution to this is to use a counting number. What's that mean, a counting number? That's a good thing to say. Aren't all numbers counting numbers? Well, what do I mean? What I mean by it is this. When I go to the bakery to get donuts, how do I usually order them? I do use money, it's true. What? Very good. I would order them by the dozen. Does that make sense? What's that mean?
Every 12.
What's it mean?
Every 12.
Good, yeah. A dozen means 12 of something. So dozen equals 12. In fact, more accurately, you could say this. It's a ratio. 1 dozen is 12 items, right? Oh, here's one. How many items in a score? If I buy a score of something. Are you thinking 407 years ago, our forefathers? You're right. No, listen, what is that? That's a famous, famous, famous speech. 407 years ago, our forefathers endeavored to, I used to have this memorized. Anyway, but now we are embattled in a great, it is 20. Very good. So by the way, there's an interesting thing. 407. I just try to imagine a current President of the United States speaking in this kind of flowery language. 407. Anyway, what's that mean? 407. What's it mean?
87.
Yeah, 87 years ago. Yeah, that's all Lincoln's saying. 87 years ago, we made a country. Right?
Are you kidding me? I didn't even know. I never knew it.
Yeah, that's all he's saying. 87 years ago, our forefathers started this country. Don't judge Lincoln. What? Oh, we're better than Lincoln now. I see how it is. Yeah. He wrote this in 18 what?
87 years after.
Yeah, so what's that? 1776. But it was Battle of Gettysburg, and I don't know. Anyway, I should know this. But the point being, 407, 87 years ago. What's another one? Yeah. Oh, there you go. 1 baker's dozen is how many?
13.
Very good. I read once, and this may be completely apocryphal, but that there were severe penalties if you shorted somebody. So like if you, in like the British system, if somebody ordered something and you shorted their order, you could face really heavy fines. So bakers got in the habit of always putting one extra in just for kind of like safety's sake. I have no idea if that's true or complete BS, but I have read that before. But it strikes me as one of those things just a little too cute to be true. I think you always have to be very wary of these things. They go, well, where this comes from is blah, 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 blah. And like 9 times out of 10, the story they have to explain a saying is just complete BS. So that's the story I've heard. True or false, couldn't tell you. Yes?
Maybe it's because the baker's dozen is them giving themselves a dozen after the job is done, and they're giving themselves an extra.
Oh, like 12 for you, 1 for me kind of thing? Like how I used to bartend. Anyway, I'm kidding. I took 2. No, never. All joking aside, I never drank on the job until becoming a teacher. I'm kidding.
That sounds really sarcastic when you said I'm kidding.
Joking aside, I have never drank on the job.
You're not looking at me in the eye.
Listen.
All joking aside.
Am I squinting like that?
Yeah,
All joking
you are.
aside, no. I have had many jobs and I've never had a drink at one of them. Scouts honor. All right. So no, like
The fact that you have to reassure me makes me not believe you.
sorry?
The fact that you have to keep reassuring it makes me not believe you.
Believe me or
I'm
don't.
kidding, I'm kidding.
I might be drunk right now. So for calculations in this course, we're going to use a process called dimensional analysis. And this is probably something you haven't done before. I didn't learn this until first year university, and it changed my life for the better, because instead of memorizing a bunch of formula, which is an awful thing to do, like 70% of the math you do in science, you can do using the same process. And it involves a common sense approach to thinking about what the units mean. Does that make sense? And it comes from the idea that when we multiply and divide, sometimes things cancel each other out. Does that make sense? If I did 4 times 3 divided by 4, without even having to use my calculator, what does the answer have to be?
3.
Yeah, why? Because 4 divided by 4 is just 1. Or 1, right? So if I took the number 3 and I made it 4 times bigger, right, by multiplying by 4, and then I made it 4 times smaller by dividing, it would have to be just itself. Does that make sense? I didn't have to do any math. And I can do that with really ugly numbers. This is just me scribbling, but if it helps your thought process, you can. If I did 3.27 times 1.18 divided by 1.18, those are ugly decimals. That's tough multiplication. What's the answer? Skadoosh? So is that a word? Okay, fair enough. So what's the answer? 3.27. But that's really ugly decimal numbers. How did you know that? Yeah, because when we divide something by itself, it's canceled, right? Well, let's keep this in mind then. Because what I'm going to say is this. In dimensional analysis, we start with a number and a unit. And what's a unit? What do I mean when I say a unit?
It's how many of a certain thing?
Maybe, but give me an example. What's an example of a unit? My number could be 7. 7? Okay, let's use that as our example. 7 centimeters. Okay. And then, when we do dimensional analysis, we are always multiplying by a ratio. We multiply by a fraction. Does that make sense? Because when we multiply by a fraction, the neat thing is we are multiplying, and then immediately after we multiply, we are dividing, because that's what a fraction is. It's division, right? So when we multiply by a fraction, we multiply and then divide, just like we did up here, right? We multiplied and then we divided. So here's what we can do. We can multiply by the new unit that we want. So whatever math I'm trying to do, if it goes from one unit to another, I can put the new unit on top. And what am I going to put on the bottom? The original unit. So let's be here. What if I wanted to convert 7 centimeters to meters? I would put meters on top, and I would have to put what on bottom? Centimeters. Okay, so we multiply by a fraction, and on the top we put the new unit that we want, and on the bottom we put our original unit, the unit we started with. Now the only thing we have to do is make sure that this fraction is true, that the numbers we put in it are true. This has to be a fact. It has to be factual. Right? That's important. Now, the nice thing is meters and centimeters, we know exactly what that fact is. How many centimeters are in how many meters? Who knows that relationship? 100 centimeters is what? Good. So we can just put those numbers in here. We can say that there is 1 meter for every 100 centimeters. Here is where this becomes useful. For this to work, centimeters times meters would be centimeters meters. That's weird. But then when we divide by centimeters, we have now divided centimeters by itself. And when we divide something by itself, it becomes, it cancels. It just becomes 1, so it just cancels out. So centimeters disappear. What am I saying? It sounds like you're saying it's a douche. And I'm like, it's a perfectly fine number. You should be nice to it. Skadoosh. All right. Can I say, when anyone says that, they kind of look like Mr. Cleves. Say it again. Like there's something that happens to your facial expression when you say that word, that you become, shall we say, Clevesian. And now we can do the math. 7 times 1 is 7. And then divided by 100 is 0.07. And what unit is left? Both centimeters canceled. All I'm left with is meters. This works for any unit conversion. And you're going to see it works for a lot more than just unit conversions, as long as you know a fact. And the fact does not have to include a 1. If you know that a 12-inch ruler is 30 centimeters, because they're like on the same ruler, you could use that as your fact, 12 inches and 30 centimeters. And you can use that fact to convert from inches to centimeters. I'm going to give you a worksheet tomorrow with completely made-up units, things like zoodlezaps and zaffroxes. And you're going to do all kinds of conversions from one made-up unit to another made-up unit. Make sense? Doesn't matter. Doesn't matter what the unit is. As long as your ratio is a fact, and as long as the units cancel, your answer will be true. And because the universe works on mathematical principles, you're going to discover that there's all kinds of problems that your friends who go to Laura Secord and BT are memorizing formula that look a little bit like this. N equals M over big N. Oh, that's a great formula. I'm never going to get that confused. N equals M over N. Oh, what if I rearrange it to solve for M? Oh, well then M equals N times N. What if I go solve for the other N? Oh, well then N equals M over N. It's awful, right? I mean, it's Satan itself. It's impossible to keep track. We're going to teach you rather to understand it, all right? To set your units up so they cancel, and you'll always get a true answer. And it doesn't involve a trick. There's no black box. I'm not drawing a triangle with letters in it, right? And saying like, cover up the one you want. None of that nonsense. Have you ever seen that before? Yeah, we're not doing that. We're not doing that. We're going to understand why the math makes sense with the science. Does that make sense? Instead of just saying, here's a formula, we're going to always understand exactly why this math is going to give me the answer I want. And we're going to do that using dimensional analysis. So let's try this. How many people are in a crowd of 32.5 dozen people? Well, we always start with our number and our unit. So in this case, what number have we been given? 32.5, and that number is what? Dozen. And more to the point, I'm going to say dozen people. You're going to discover that I am very specific with my units all throughout chemistry, because a dozen people is not the same thing as a dozen donuts. If you eat the dozen donuts, you'll get a stomach ache.
But
right? So anyway, moving on.
I think
Now, I don't want to know about dozen people. I just want to know about people. So my new unit is people. What do I put on the bottom of this fraction again? Dozen people. That's right. And now I just need to put a fact in here. So what's the fact? Good. So where's the 12 go? Where's the 1 go? No, you said it. 12 goes with people. Good. Yeah, no, you said it exactly right. I was just reinforcing. I wasn't correcting. And the 1 goes with what? The dozen. Good. We always have to make sure that fact is correct. And it helps to say it aloud, because you will immediately notice if you've put the numbers in the wrong place. Can everyone lift your pen? Let's put your pen down. Don't write what I'm about to write, because I'm about to make an intentional mistake. Okay, so let's not write it down. So if I put it like this by accident, easy mistake to make, right? Say it out loud. Oh yeah, 1 people is 12 dozen people. Does that make sense? No, right? If you say it out loud and it sounds ridiculous, then it's the wrong setup. Does that make sense? That doesn't make sense. That's absurd. She was so upset that I did that she started screaming. I hope everything's okay. I shouldn't have made a joke. So there are 12 people in a dozen people. Makes sense, right? And now, what do we get when we do that math? Well, 32.5 times 12 divided by 1. You'll probably want a calculator for that. I don't know how good your 12 times table is. 325, 2 times that is 65. So 3. So 385. Is it 390?
Yeah.
390. That's good. I was going to say 400, so I'm glad for that.
Hey, you found it.
Yeah, we're going to get to that in a minute. So now, quickly, what units cancel here? Yeah, because we're taking dozen people and dividing it by dozen people. That unit cancels. By the way, remember, we have always, whether you've realized it or not, you have always multiplied not just the numbers, but the units. You know this because if you take a square that is 3 centimeters by 3 centimeters, the area of that square is 3 centimeters times 3 centimeters, which is 9 centimeters squared. You've always been multiplying the units as well as the numbers. You just haven't been thinking about it. Right? And when you took the square root of 9 centimeters squared, you got 3 centimeters. Well, because the square root of 9 is 3, and the square root of centimeters squared is centimeters. So this whole time, you've been multiplying and dividing units. You just haven't been thinking about it. Now we're going to think about it. And what unit remains then? What unit goes on my answer? What is it? People. Now let's talk significant digits. By the way, how many significant digits here? 3. Okay. Now I want you to be careful. I want you to remember our rules here. How many significant digits on 12 and 1? Infinite. Why are they infinite? Good. Because when we say there's 12 people in a dozen, we don't mean it could be 11.9 people in a dozen. If I bought a dozen donuts and there were 11.9 in there, I would not feel like I'd gotten my dozen because it rounded to 12. I'd feel grossed out that somebody ate half my donut. Right? Right?
Wait, what was the thing?
Donuts. If I ordered 12 donuts and got 11.5 because one was half eaten, I'd be grossed out. Yeah, right? That'd ruin your whole day. So how many significant digits in the question then? What's the least number in the question? So how many should be my answer? 3. Hey, what's it look like are in my answer? Yeah, so how am I going to address that? I could put a decimal at the end, but we said that's kind of uncouth. That's kind of uncouth. So what notation could I use here? Oh, I totally could. What's this in scientific notation? 3.9. How many sig figs do I want? 3. So 3.9. Good.
Times 10 to the power of something.
To the power of?
2.
2. Good. Why 2?
Because 10 times 7 is 100 times 3.9 is 3.90.
Yeah, very good. We move the decimal 2 places, or we multiply it by 10 twice. Absolutely. And what's the unit? People. Good. So, So how many people are in a crowd of 32.5 dozen people? Well, 3.90 times 10 to the 2 people. People.
I'd actually get so mad if someone told me that.
Speak English, please.
Yeah, you have what? 2.35 times 10 to the 2 people attending your
We
school.
only have 235 kids at our school.
Daily attenders in building.
So is it teachers too?
No, that's students. That's student body. I think your teaching staff's in the 30s, and support staff is probably about
Does
20.
it count people in the programs or no?
Well, it does. So, but they are in the total population, but they aren't necessarily daily attenders, right? So they beyond that, our actual student population is like 325.
That's how many kids are at our school?
That includes people in all. That includes people on like home build projects.
Oh.
It includes like all kinds of different things. So all kinds of reasons why different students are attached to our building but not in our building. That includes some students who only have a co-op, right? So they're only in our building on co-oping class days, and other than that are just out in the population. So it includes people for a lot of different reasons. Okay. Shh. Oh, this one's boring. Let's just change this question.
I was already working on that.
13 score years. Geez, you know, that's when you undercut your own example by telling stories early on in the lesson. What a shame. What a shame. So I want you, now I know that you could just do this in your head, but I want you to set it up because soon enough we'll be dealing with numbers that you can't just do in your head. Okay, so I totally understand that you can multiply by 20 in all likelihood in your head because you're clever kids, but I want you to pretend you can't. The trick is to multiply by 2 and then move the decimal. Right? Double it and then add a 0.
Oh wait, that's not the right answer. I see that
Wait, where do
now.
you start?
Sorry? Yeah, do this. And I want you to set it up properly. Well, that's not going to happen anytime soon, I can assure you.
Yeah, that was.
So how about you stop talking and get to work? You really be talking to me?
Four.
Wait, so score is specifically talking about year? Or
Not necessarily in this case. So do you see how I do the subscript in the unit? Score is my units, and then years is what we're talking about. And by the way, you're going to see that a lot. Like later on, you're going to see me say things like grams of calcium. Does that make sense? Or kilograms of gold, or milliliters of water. That's right. So the unit and then the subscript tells me what I'm talking about, which is important because grams of water are not the same thing as grams of rat poison. You drink 10 grams of water, you've had a delicious little treat. You drink 10 grams of rat poison, you have a problem. Does that make sense? So it's not enough to say grams. Grams of what, right? So likewise, it's not enough to say score. You have to say score of what? Score of years. Okay, so I start with 13 score years. What am I doing? Well, here's what, again, dimensional analysis takes a bit of practice to get used to. Once you get it, it'll save your life. You'll love it. But what we're always going to do is get rid of the unit we don't want by putting it on the bottom and put our new unit that we want on top. So I don't want to talk about score years. That's the unit I want to get rid of. So that can just go down there. Instead, I just want to talk about years. And I always put the units in before I put any numbers. Does that make sense? Write your units in with no number. So I just leave a blank space for my numbers. In dimensional analysis, we think about units first. We make sure they make sense. Then we put numbers in to make it true. Okay? That's right. So now, what numbers go in here? How many years are in a score? How many score are in a year? What numbers make this true? 12 is a dozen. Right thinking. 20. Good. And is it 20 score? Okay, so 20 years is how many score? 1. And again, this won't necessarily always be 1, right? So far it's been 1. But, and this would work if I said 60 years is 3 score. It'd be a weird thing to put, but the math works. Okay, now, if you look here, what unit's going to cancel? Well, we have score years divided by score years, and that leaves only what for the answer? Years. Whoa, that was weird. And what's the number? 13 times 20 divided by 1. What's that give us? 200, 260. Good. And let's take note, how many sig figs should we have? Yeah, because this is 2. 2 sig figs. I'm going to try to be consistent from now on. I'm going to always use green for significant figures stuff, and that's all I'll use green for. Okay? That's just, I'm going to get in that habit so you guys are used to seeing that. If I put green arrows on stuff, I'm talking about significant digits like from today to the end of the course. That way I don't have to highlight first. Is that fair? That's just going to be like our little code. We're always going to stick with it. And how many significant digits in 20 years? Infinite, right? Because we're talking about 20 years exactly is 1 score exactly. That's true by definition. Likewise, 1 score is infinite. So how many significant digits should my answer have? How many? 2. Now, as it happens, this is nice. That is 2. If I wanted to be really unambiguous so nobody was wondering about that 0, how can I answer this question?
2.6 times 10 to the power 2 years.
Yeah, I could do that, but both answers are good because 260 years also has 2 significant digits. So these are both good answers. I like them both. You probably like the top one better because it's a little less work to get.
But you probably like the bottom.
Oh, no, I probably like the top one better too. I like scientific notation, but come on, we don't always need to use it, do we? But they're both good answers. Okay,
Good practice.
now, this process, we're going to practice a lot. Oh, golly, are you going to do a lot of these? Like so many. Oh, gosh. Like every single question you do from now to the end of the course, you're going to do some dimensional analysis. And like, the thing is, in most questions, you won't do like 1 row like this. Sometimes there'll be like 7 ratios. Because you'll just keep going. We could keep going, right? Now what if I wanted to go from years to, like, you don't have to write this, but just as a case in point. What if I wanted to get to how many seconds this is? I know it's 260 years, right? Now, do I know how many seconds are in a year? No, but could I get smaller? What do I know? What's that? I could go weeks, months, but I could probably go right to days, right? I mean, I could go months and weeks, but I could go right to days. How many days do we have? Yeah, and specifically, actually, 365.25 days in a year, right? Because every 4th gets an extra. So there's 365.25 days in 1 year, right? Now what would I do to keep going? Well, just add another fraction. Years is canceled. What do I want to get rid of now? I want to get rid of days. And what should I go to from there? I want to eventually get to seconds. Yeah. Great. How many hours in a day? 24 hours in 1 day. Cool. Now days is canceled. If I stopped now, I'd know how many hours there were. What could I do next? Okay. And so I would cancel hours and I want minutes, right? What numbers work there? 60 minutes in 1 hour. And then what would I do? Cancel out the minutes and instead I want, and what number goes there? 60 seconds in 1 minute. It's actually really easy, isn't it? We just write it all out. And then when it came time to do this, I'd just punch into my calculator. 260 times 365.25 divided by 1, times 24 divided by 1, times 60 divided by 1, times 60 divided by 1, press the equal sign, 1 step, 1 use of the calculator, boom, we get the answer.
Would you skip those steps and go from 260 to 60? Like 260 years?
If you knew how many seconds were in a year, yes. So yes, if you knew how many seconds were in a year, if you're like, that's a number I've always known and I've just been waiting to use it, then yes. But if not, you have to show all the middle steps. Because all you need is a fact that's true. By the way, you could just Google how many seconds in a year, but really, if you're going to Google, why wouldn't you just Google how many seconds in 260 years and get the whole answer, right? But as long as you know a fact, you can jump from any unit to any other unit. We did these steps, and by the way, it could have been more complicated, right? Like, which is fine, but we were suggested like we could go straight to months. Okay, but that's just adding layers of trouble, right? What's the answer we get, by the way? Did anyone do this?
Yeah, it's 8.204976
Well, how many sig figs should we have?
to the power of 9.
We should just have two sig figs, right?
So it has to be rounded.
2 sig figs. So how many 2 sig figs is it? 8.2 or 8.3?
8.2
8.2 times 10 to the
power of 9.
seconds. So there's 8.2 billion seconds in 260 years. There you go. That's kind of cool. And that, honestly, that math's a little clunky, but it's not that bad, is it? Dimensional analysis versus what you would have done in the past, which is like done each of those calculations stepwise, written the answer down, then do the next calculation, write the answer down, then the next, right? We're learning to think of math, and the reason it works is that the units all cancel. And the only unit left is seconds. So as long as each of those ratios is true, you could keep going. If you knew how many seconds an average Taylor Swift song was, you could define 260 years in average Taylor Swift song lengths. Nothing to it. That's how I speak about all my time. I don't measure my birthday. I measure my 10 billion Taylor Swift songs days. I don't know. Anyway, yes, go.
Can you just multiply all the top numbers by each other? And
As it happens, you can always skip a 1. Yeah, because 1 doesn't change a number. When you come across a 1, it is not mathematically necessary to divide or multiply by 1. But keep in mind that it won't always be 1 on the bottom, right? It happens to be here. So yeah, you could save that time. Just be careful. Don't think you can always skip the bottom, right? You skip the bottom here because it's 1. Exactly. Okay. What does any of this have to do with chemistry? Well, our friend Avogadro.
He's not my friend.
May I mention, it was his last name, but that's neither here nor there. A massively underused first name, I think. I'm just saying that, you know, when the time comes, maybe you have children, maybe you don't, but Avogadro Blaze, got a little ring to it. Don't you think? I think. Well, avocados are delicious, so. What?
I don't like the texture thing.
Wow.
That was such an.
You can like spread it on toast. It's so delicious. Okay, well.
It's not.
What?
If there's
You know what that was?
Okay, that's fair. Okay, anyway, do you like guacamole? Like, do you not like it at all? Or in certain settings you like it? Interesting. Okay. Anyway. Here's the deal. We said atoms are really small. Atoms are really small, which means for us to use them, we're going to have a lot of them, right? When we do a reaction in the lab, we've got a lot of them. So we need a big counting number. Dozen won't cut it, right? A dozen atoms is still very, very, very small. Yes?
Can you just like measure the element you have and then divide it by
That's actually precisely what we're going to do, but we'll get there. Because as it happens, that's what we're going to do tomorrow. But as it happens, when we do that, we get a special number. We get a special number. And the number we get is this number. This number is the number of atoms that we get if we work with really convenient weights of our atoms. Specifically, if the weights, we'll learn about this tomorrow, but specifically if we use those weights, only instead of atomic mass units, we use grams. This is how many of those we have. So this number, 6.02 times 10 to the 23rd. Now let's keep in mind that is 6, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, running out of paper, 20, 21, 22, 23. That many atoms. That's a lot. If you want to have a fun little exercise, figure out how many years it would take to count that high if you can count a number every second. that can be a little dimensional analysis homework question for you. How many years would it take to count that high, counting one number a second? If you show up with that tomorrow, I'll give you a little prize. Fun fact, long time. Now, it's a big number, but it's still just a number. Does that make sense? You can have a dozen donuts, which means you have 12. Or you can have 6.0 times 10 to the 23rd donuts, which is more donuts than there are stars in the universe, or vastly more than there are grains of sand on the planet Earth. All the same, there's a name for that. And the name we use, because to call it an Avogadro, that'd be a big long word. So there's a term we use, and I've never bothered to look up why we use this word. Maybe I'll do that tonight. We call this a mole. If you have 6.02 times 10 to the 23rd of something, you have a mole.
Yeah, I thought it was called mold because
Oh, that is wonderful.
That is avocado.
Yeah, there you go. Oh, you see, Kevin? Brilliant. So now listen. Shh. Listen. There are moments in your life that we usually define, before or after moments. If you're Jewish, a Jewish male, you think of your life before and after your bar mitzvah. If you're Catholic, I suppose you think of your life as like before and after confirmation. If you get married, you probably imagine what your life was like before and after you're married. Likewise, you will, for the rest of your life, delineate your life as all the time before you knew what a mole of something was, and all the time in your life after you knew what a mole was. You have, without realizing it, just had a transformational moment in your life, and you can never step back. You've stepped, well, that's okay. Like I said, you may not know it yet, but you've just stepped into a whole new level of thinking about the world around you. Congratulations. So, here's the deal. It's a really big number, but if I have a mole of something, I have 6.02 times 10 to the 23rd of that thing. It's just like dozen. Does that make sense? So when we use mole, just like when I said dozen, I'm always going to have to put a little subscript on that to say what I have a mole of. You don't just have a mole, you have a mole of something. Just like you don't have a dozen, you have a dozen of something. Does that make sense? A mole is simply a counting number. Just like dozen, just like score, just like couple, right? Just like, so, there we go. So if I had 4.3 moles, and when we write it as a unit, being lazy, we leave off one letter. The word is mole, M-O-L-E. The short form for moles, M-O-L. Yeah, efficient, right? And in this case, we're talking about carbon atoms. So I'm going to put 4.3 moles of carbon atoms. Units are important. We don't get lazy with them. We write very specific units. Does that make sense? Because a mole of carbon atoms is not the same thing as a mole of zinc atoms, is not the same thing as a mole of pastries or magnesium. Now, with dimensional analysis, we always write a fraction after it. And on the bottom, we put what? Yeah, we put the unit we want to get rid of. In this case, mole of carbon atoms. And on the top, I'm going to put my new unit, which is I just want to know how many carbon atoms. Yeah, by the way, you're going to need a calculator. Do you mind passing those around? Even if you've got them, pass along. Thanks. Shh. So what unit am I going to put on top? I don't want to know how many moles of carbon atoms I have. I just want to know how many. I don't want the answer. I want to know how many carbon atoms. Now, it comes time to use Avogadro's number. And we said that 1 mole of something is how many of that thing? Very good. 6.02 times 10 to the 23rd power. So there's 6.02 times 10 to the 23rd carbon atoms in 1 mole of carbon atoms. There you go, sir. There you go. Oh, I just gave you one. There you go. Look at me. Well known for my sweetness and toughness. Those are the first 2 things people notice about me. There you go. And again, let's make sure we all know how to use our scientific notation buttons, right? Very important, very, very important. The output will probably show you, most calculators show you with an E, though some actually have a little times 10 to the thing on it. Yours actually says times 10. Okay, so we're not punching it in right. So show me how you put it in.
I'll give it back to me in scientific notation. Yeah.
What do we have to do? 4.3. Yeah, times, keep going. Sorry, I just wanted to see the question. 6.02.
I put that.
You put what?
Yeah, I got it.
Yeah, press that again for me.
scientific notation.
Yeah, so E23 equals 1.
Oh, now I got it.
Okay, so it must just been how you punch in. Did we get an answer? Yeah, trust yourself. Okay, what does the readout on your calculator say? Obviously, everyone's a little different, but what's the readout on your calculator say? Yeah, give me the whole thing, just what it says.
2.5886 times 10
So yours shows times 10 to the... Great. The yellow calculators, what does it show?
2.586 E24 or 23.
Great.
24.
Does it say 24?
Yeah.
That makes more sense. Yep. Good. So that's probably what your calculator says, right? What does that E mean? Yeah, and again, if your calculator already says times 10 to the power of, great. That means times 10 to the exponent. Now, if that's the calculator output, what's my answer going to be? How do I write my answer? Yep.
You would like 2.5860.4 Covenant.
All right. I don't like it. What don't I like?
Right.
2.6 times 10 to the 24th. And what? Carbon atoms. All right. And I'm going to tell you a couple things right now. One, if you don't obey significant digits, I'm going to yell at you with my pen. I'll use all caps. That's yelling with a pen, right? If you don't give me a unit, I will not give you a mark. Any answer that doesn't have a unit isn't an answer because I have no idea what you're talking about. And I know that sounds pedantic when there's one step here, but when we get to questions that involve a bunch of different chemicals and things like that, I'm not just saying this to be difficult and a pain, though I love being difficult and a pain. It actually becomes impossible to look at, you know what number you're talking about because you did the math. But for me reading it, if there's 6 different chemicals in the question and you've done all this math and there's just a number at the end, I have no idea what chemical that is. I have no idea what unit it is. I don't know what you're talking about. Does that make sense? So from this moment moving forward, every time we do a question, we're going to make sure that we have the appropriate unit at the end, and we're going to make sure that we've obeyed the rules of significant figures. Yes?
I picked up the challenge.
Okay, show me after. Show me after. So this has 2 sig figs. 1 mole of carbon atoms. That is, of course, because it's just counting. But this is not infinite. Because it is this, I should mention this. Avogadro's number is a decimal that goes on and on and on. So I've given it now to you for 2 decimals. When you get your formula sheet, it'll actually have it to like 12 decimals. So if you need more sig figs, you've got them. Does that make sense? So as we've used it here, how many sig figs does Avogadro's number have? Just 3, right? 6.02, 3 sig figs. But if you need more sig figs, you need to use a bigger version of Avogadro's number. Yes?
Like if you have like 4.333.
Yeah, this will limit. This 6.02 does limit. All right, and that's worth noting. Yeah, so if you like Google Avogadro's number, it doesn't stop at 02. It keeps going. For now, for these questions, we're going to stick to 3 sig figs because it's enough and there's no need to make it more complicated. When we get to questions where we're going to need more than 3 sig figs, we will use more than 3 sig figs. Okay, I want you to try the next one. How many moles are there if you have 4.55 times 10 to the 24 atoms? We're going the other way this time. See if you can set it up. See if you can answer it. This will be the last one we do in class, and I want you to finish all of these questions for homework. Yeah, let's see it.
I calculated and it's 1.89976752 times 10 to the power 3 or 1.90 times 10 to the power 1.
Okay, let me take a look. So we did 6 numbers per second. You're super close. But. Oh, I see. You put per on the bottom, so that cancels with 1 on the top. So this would be numbers per. Yeah, it becomes numbers per year. Put that down there, right?
And this is how many numbers said per year. I've had to do these all.
Let me think for a second. Okay. Can I tell you how I would do this? I would say 6.02 times 10 to the 24. No, right? That's okay. You're right. That's weird. In 1 second, right? And then we want to leave numbers right where it is. So let's see. Let me think. I haven't thought through this. I think your process is good. I just have to think through whether the units are not. Show that to me again tomorrow, okay? I'm just having a moment right now. Sorry?
This is why I did it.
Yeah. What I would say is this. Try it this way. Try, because we know that it's 1 per second, just try it at 6.2 times 10 to the 23 seconds. Because we know that's what we've used to, right? And then go from there. See what you get. In other words, it'll still be a long time, but it should be fewer years than it is seconds. So what you figured out is that you've told me that if we can say 6.02 times 10 to the 23rd numbers in 1 second, we could say this many numbers in a year, which is true, but not what I asked. And also, we cannot say this many numbers a second because it's a lot. Does that make sense? So we're not saying these numbers per second. We're saying one of them per second. So it takes that many. But you're on the right track. In other words, all of this is good.
Every single part of this was perfect except for the beginning.
Well, except you're trying to cancel seconds. So where do seconds have to go? Not on the top. Yes, good. Good. Yes, come in. Okay, what? Great. You want to come out lunch and we'll get those ones done? Yeah, it should take like honestly 5 minutes. That's perfect. Yes. Well, are there that many moles in 1 atom? Or are there that many atoms in 1 mole? Does that make sense? Yeah, so we always, and that's why it helps to say it loud. So sorry, I got sidetracked because Alondra had an interesting answer to my question. So let's try this. What's my given information? Sure, but what was I given in the question? You're right, like you're totally right. But what did the question give me? Yep. Okay, so we have a pile of atoms in front of me, and I'm told that it is 4.55 times 10 to the 24 atoms. But what I want to know isn't how many atoms. I want to know how many moles. So what do I have to do? Yep. Yeah, and specifically a mole of atoms. Yep. And we're putting just the atoms on the bottom. Very good. Again, it's easy to switch, but it helps if we say it aloud. This tells me that 1 mole of atoms is 6.02 times 10 to the 23rd atoms.
You only have a 3.
Oh, well, that's not right. Just checking if you're paying attention. And what do we get when we calculate that out? Great. And so the raw output from your calculator is 7.558 E20 what? Oh, no E, just 7.558, right? Okay, and it keeps going. What should I put as my answer then? 7 point what? I don't like 7.6. 7 point? Sure, why? Yeah, because here I have 3 sig figs. How many do I have here? 3. And what about this one up top? Yeah, that's a spaceship, I believe that was. We have infinite sig figs because it is a cardinal number. It's a counting number. And keep in mind what units cancel. Atoms cancels with atoms, leaving me with moles of atoms. All right, guys, get the rest of the sheet done for homework. Have a wonderful day. Be kind to one another. Don't do anything Alondra wouldn't do.